Okay, now we look at the second measure of the center, right? Again, with some different meaning of center, but still it is a center. So you already know the median is actually the value below which we have 50% of the data. Right? Once you put the data in the ascending order, you can find out a value below which 50% of the data lie, and the other above that the other 50% will lie. Right? So that is actually, in that sense, that is the middle of the data set. Right? The point that divides the data set into two equal parts, so that the first part will have 50% of the data and the second part will have 50% of the data. Right? So how do you find out the median if you have a list? If you have n observations, first of all you have to put the data in some order, ascending order or descending order. Right? And then what will be the position of the median? Which number? I mean, at which position? The position will be given by n plus 1 over 2. Right? If you have, for example, 10 observations, then 10 plus 1 is 11 divided by 5.5, right? So that means the median is going to be in the middle of 5th and 6th observation. Median is going to be in the middle. If n is equal to 11, then n plus 1 is 12, divided by 2 is 6, so then the median will be the 6th observation in the ordered data set. Right? So many people usually forget to put them in order, they will just find out the 6th value in the list. That is wrong. That is not the median. Right? After you put the data into the ascending or descending order, then the 6th point, if you have 12 observations, 11 observations. Right. So, but generally, if your histogram, most of the times, your histogram can be one of these three shapes. So depending on that, we can find out relative positions of those two centers that we talk about. One is the mean, arithmetic mean, the other one is the median. So if you have a kind of symmetric doesn't have to be bell-shaped. Even if, for example, if the distribution is something like this can be symmetric. It's called uniform distribution. Even if the distribution is like this, it is still symmetric. Right? If that kind of shapes are very rare, but there are situations that kind of shape is called bathtub shape or U shape. Right? So all those symmetric distributions will have roughly the same value for mean and median. Right? Roughly the same. Like for example, here 50% of the data below this number, 50% above that. Right? So therefore, mean will also be roughly the same. For symmetric distributions, therefore, mean and median are roughly the same. Let's consider this kind of distribution. So it mentions here the average is bigger than the median. Why is that? The average means here the arithmetic mean. Arithmetic mean is usually bigger than the median, right? So the median will be somewhere here, for example, say 50% of the data here and 50% here. So the area has to be divided into two equal parts at some point, so that will be the median. But the mean will be somewhat larger than that to this direction, maybe somewhere here. That is the balancing point now. So there are some values here, even though with small weight, the moment created by is large because the distance is large. So therefore balancing point has to be moving to that direction. Therefore the mean will be larger than the median given. So positively skewed distributions, therefore generally mean is larger than the median. Similarly for the negatively skewed ones, mean will be smaller than the median. So those are the relative sizes of those two depending on the distribution. As I mentioned, usually people use the mean as the center if they think that the distribution is symmetric, or when you draw the histogram, if you see that the distribution is roughly symmetric. Of course, practically you don't have exactly like this, roughly this shape. Right? On the other hand, if the distribution is skewed positively or negatively, then people usually use the median as the center of the distribution or as the average in some other sense. Right. So here's an example, the income of family income of US people. The histogram is given here. So they have calculated actually. They have calculated the median was $12,000. The mean was $13,800. So you can see that it is actually a positively skewed, and you can see that the mean is larger than the median, as it should be, right? Median mean is larger than the median because it's positively skewed. This is another example. This histogram shows the weights of women in the second example in the previous survey. The vertical line marks the average, or this is actually the arithmetic mean, so that is the balancing point of this picture. So where would you take the median? Median will be less than this or greater than that. Median has to be on this side, smaller than that, right? To the left of that. Okay, so that's all they talk about the median actually. They have talked very little about the median. So the next thing is the standard deviation. Now, once you describe the center in some sense or the location in some sense, in order to describe further, you have to mention how fat the distribution is, how wide the distribution is, right? How wide the range of the data is, right? So there are again large number of measures people use. One is the range. So these are the measures of the something called the dispersion. Right? Dispersion is the word. Spread, another word. Right? Measures of the spread. Range is one, and the second one is something called the variance. And then standard deviation comes from the variance. And there is another thing called quartile deviation. There's another thing called interquartile range. So all these are used in different situations as measures of the spread of the data. Right. So here in the book actually they talk about the standard deviation. But before getting the standard deviation, we have to get something called the variance. The range is of course a very, very primitive measure of the dispersion. It talks only, it uses only the maximum and the minimum. Right? So for a data set actually you might have a data set like this. Minimum may be here, some maximum may be here. So maybe the data are spread like this. Or you may have another data set with the same minimum, with the same maximum. Right? But all the data, all the other data may be somewhere there. Right? So if you use the range as a measure of the spread, you get the same value. Right? Same spread. But of course you can see that the spread is not the same. Right? Here these data are somewhat uniformly distributed in that range. Here they are distributed very close to that. So therefore we can see that very clearly range is not a very good measure of the dispersion of the spread. So therefore when we talk about the spread actually it is meaningful to talk about the spread around your center. Right? You have already chosen a center. Right? Depending on the shape of the histogram, probably if the histogram is symmetric, you will choose the mean as your center. Once you selected the center, mean as the center, then you want to talk about on average how far away the data from the center, right? If you have chosen median as your average or the center, then you might want to talk about how far away on average, how far away the data from that center, from the median. So depending on that, there are choices. For example, if you want to talk about the distance to your observations on average from the mean, you use one of these, variance or standard deviation. That gives you the kind of average distance or average distance square from the mean. Right? So if you have chosen mean as your center, generally people use one of these as the measure of the spread. If you have chosen the median as your average or the center, then people usually use one of these two as a measure of the spread. Right? The book in this chapter talks about only the standard deviation. I think they are talking about this one a little later. So let's talk about the standard deviation. Before talking about the standard deviation, actually usually we talk about the variance. I don't know, for some reason the book doesn't talk about the variance. They have directly come to the standard deviation. But the variance is something like this. Once you have calculated the mean, suppose you have x1, x2 up to xn individual observations, and suppose x bar is the arithmetic mean, then the distance between x1 and x bar will be equal to x1 minus x bar, right? That is the distance, right? For example, this may be x1 minus x bar. This can be positive or negative depending on whether x1 is smaller than x bar or larger than x bar. And the second distance will be x2 minus x bar. Like that you can look at the distances, xn minus x bar. So it's not the variance yet. So if you want to look at the average distance, what you can do is you can just add them up and divide by n. Right? So that will give you the average distance from the observations to the mean. Right? So if the average distance is a good measure, then for this kind of data set, for example, suppose you have a data set like this and another data set like this, say for example, for this the average distance should be larger, for this average distance should be smaller, right? Mean will be somewhere here. But can we get that kind of two numbers, large number for this data set and small number for this data set, if we use this measure? No, why? You cannot get it. Yeah, no matter what the actual spread is, this is always zero. It's always zero. So therefore this doesn't give you any idea about the actual dispersion, the spread. Right? What you need is something like this. For example, you need some measure that you will get large value for this, small value for this. Right? Some measure giving you two values like that. That's what you need. Right? So, but this one doesn't give you that. Always it is zero. Therefore, average distance, some of them will be positive and some of them will be negative. They will cancel out. Mathematically, you can prove that actually is exactly zero. It's not difficult to show that. Right? So that doesn't work. So some people therefore look at, instead of the distances themselves, they look at square distances. x2 minus x bar square and so on. xn minus x bar square. And then add them up and then divide by n. Right. So that gives you the square distances from the mean on average. Right? Square distances to the observations from the mean on average. Right? So once you have x bar here, then for this one, x1 minus x bar square will be a positive value always, so they don't cancel out now. It will be a very large number. Right? If for this one, it will be a smaller number than that, and therefore definitely for this thing you are going to get a smaller number for this and then this one. So therefore, it is a reasonable thing to look at. Right? So this quantity, average of squared distances from the mean, is what we call the variance. Right? There are two words here you have to be careful. One word is the variability. That is what the spread is, or the dispersion. The same thing. Variance is a measure of the variability. Variance is a measure of the variability. It's a method of calculating. So variance actually is a popular method. It doesn't have the weakness of cancelling out the terms. So therefore variance is used as a measure of the variability. Right? It gives you idea, but there is a weakness also. What are the weakness? What is the weakness? So what are the weaknesses of the variance?
The dimensions don't match together.
That's right, exactly. That is the main difference. It's very difficult to understand what the value gives you. For example, if you have say 25 as the value, but the unit of it will be the squared unit of your data. Right? Suppose the data are in kilograms, then x bar will also be in kilograms. Then x minus x1 minus x bar, x2 minus x bar all will be in kilograms, but when you square them, it will be kilogram square. So your variance will be kilogram square, 25 kilograms square. It's very difficult to interpret, right? What does it really mean, right? So that is why, in order to solve that problem, people take the square root of this, right? Instead of using the variance, therefore, many people use the standard deviation. Therefore, the standard deviation will have the same unit as the data. Right? So therefore, the standard deviation is defined like this: xi minus x bar square divided by n, that is the variance, and then square root, that is the standard deviation. So that gives you an idea about not exactly average distance, because first of all we have taken squared distances and then summed them up and taken the square root. Right? So it's not actually average distance, but average squared distances, and then root is taking the square root of the average squared distances. But roughly, generally it's used as a average distances in general, as a measure of the average distances to the observations from the mean. Right? So that's what you mean by the standard deviation. So in the book actually they have discussed a lot of things before discussing this thing. They are just talking about how to calculate something called the root mean square also. Right? If you have several numbers, say x1, x2 up to xn, they first define what you mean by root mean square. Root mean square, right? So it actually the practically what you do is opposite in that direction. First of all, square them, and then take the mean, and then take the square root. Right? So if you consider squares, you will have x1 square, x2 square up to xn square. If you take the mean, you have to add them up and divide by n, and take the square root. This is what you call the root mean square of a list of numbers. Root mean square of a list of numbers. So what you have for the standard deviation is actually, so this one is actually summation xi square divided by n and then square root. That's what the square root mean square of a list of numbers. The standard deviation is I from 1 to n, xi minus x bar square divided by n square root. So instead of x square, now we have squared deviances, differences, right? So if you want, you can call it, for example, di. So it's like di square, sum of di square divided by n, right? So it's also root mean squares of not the individual observation, root mean squares of the differences between mean and the observations. Right? So that is not an easy thing. Actually, mathematics students can directly understand this thing, right? So so SD is actually therefore the mean or the average of deviations, square root of the average of deviations from the average squared values. Right? So I don't think you need, I have to explain how to calculate these things and so on, right, to you. So, but remember SD has the same unit as the data. So how does it measure the, how do we use it? For example, when you are interpreting the the dispersion? Does it mean that, for example, standard deviation is equal to this thing? Does it mean that all the data are within this distance? No, that's not what it means, right? Remember, this is the roughly, not exactly, but it gives you roughly the idea about that average distance from the observations to the mean. That's all SD is, right? So the SD says how far away the numbers on a list are from their average. Most entries on the list will be somewhere around SD, 1 SD away from the average. Very few will be more than 2 or 3 standard deviations away. So this is actually kind of a empirical observation in most of the data sets, naturally occurring when you consider natural data sets. Right? Suppose the whole data set is between A and B in a large range. Right? But in most of the data sets, suppose the mean is somewhere here, mean is somewhere there, x bar. Then suppose SD is some value, say for example 5 for the data. Then most of the data will be within 5 units from x bar. Most of the data. Right? And then the remaining one will be here and here. So that is one thing that gives you, that tells you from the standard deviation you can get some idea. Most of the data, roughly in some situations, in reasonably symmetric distributions, roughly 68%, that means 2/3, roughly 2/3 of the observations are usually between x bar minus SD and x bar plus SD. This is not a rule, but that is naturally, generally happening, especially if the data have roughly a symmetric and bell-shaped distribution. Roughly symmetric and bell-shaped distribution, that is more correct, that observation. Roughly 2/3 or 68% of all the data are going to be between x bar minus SD and x bar plus SD. For this kind of normal, we talk about this thing in the next chapter actually. For normal data, we can show that if you consider x bar minus 2 times SD and x bar plus 2 times SD, like if this is 1 SD, then 2 SD will be somewhere here. So roughly 95% of the data, right, will be within these two values for a symmetric and bell-shaped distribution, practically in most cases. And almost 99.7%, almost all the data will be between x bar minus 3 sigma and x bar plus 3 sigma, generally. Right? It's not a rule. There are situations, especially if you have a skewed distribution, this doesn't apply most of the time. But if you have a symmetric type distribution, usually this is true. So therefore, in that sense, SD gives you some idea about the spread, right? From x bar within 1 standard deviation, most of the data, roughly 68% to 2/3. Right? Within 2 standard deviations, roughly 95%. So that gives you some idea about the spread of the data. So that's what is mentioned here. But remember, this is called something called empirical rule, but that is not applied to highly skewed distributions. It's more correct for symmetric, especially for bell-shaped distributions. Right. So this is the same thing explained here. So if you look at actual practical situation in the previous survey, HANDS 5, the second sample, here they are looking at the distribution, the histogram of heights. Actually not for all people, here they are looking at the 18-year-old age people, right? So age-wise distribution, because otherwise we cannot put them all together. They are different cohorts and so on. It's not meaningful to consider all the people together. These are the heights, these are the distribution of heights of 18 years of age people in the second sample. Right? So you can see that it's not exactly symmetric or bell-shaped, but roughly bell shape. And they have give the mean, they have marked the mean here, right? So they have calculated the standard deviation. The standard deviation was 3 inches. They have calculated it. So if you consider mean was 7, average was 63.5. So if you consider x bar minus 3 and x bar plus 3, you get this. And then you can find out roughly what is the percentage here. That is the area. If you find out area, they have seen that in this case it's not 68, it's roughly 72%. Right? So it's not a rule as I mentioned, but most of the data are within one standard deviation from the mean. Right? X bar minus standard deviation, x bar plus standard deviation. So most of the data, right? Here even more than 68%. Right? And if they calculate the x bar minus 2 standard deviation, they have seen that it's roughly 95%, I think. Here. So that rule is applied, can be applied generally for most of the data sets, especially if the data are bell shaped. Right. So the distribution is like that. There are many people whose heights are going to be between these two. There can be very few whose heights are more than that or shorter than that, very few people. Now, if you use a calculator to get this, you can get the standard deviation using calculator directly once you put the numbers. But usually the calculator gives you the standard deviation slightly different. They are using a slightly different formula. Instead of dividing by n, it is divided by n minus 1. So they are using this I from 1 to n, xi minus x bar square divided by n minus 1. So in the book it is denoted by SD plus because it's slightly larger than the SD value because we divide by n minus 1 there. But in the book they are using SD, standard deviation as with the divisor n here, average, directly average. But this one, there is a reason for dividing by n minus 1, something called something called unbiased estimate. The other one is something biased estimate, and I cannot explain more than that. That is the reason, right? Theoretically, there is something called unbiased estimators and biased estimators. People can show that this one is an unbiased estimator for the population dispersion or population spread. Actually, what we can show is not the standard deviation. If you define the variance using this is a kind of variance. When you take the square root of that, that becomes standard deviation. People can show that this quantity, usually called the standard sample variance. Sample variance is an unbiased estimator for the population variance. Right. So when you take the square root of that, that becomes SD plus. So you can, if you use a calculator, you get SD plus value. So SD can be obtained using this formula like this. But it's not necessary actually. You are not going to calculate like that, right? So that's all in the book about the average and the standard deviation. So as a summary, what we discuss? We discuss about two types of averages, right? One is the actually they are using the average word for the mean only. So two types of centers, right? Average, according to the book, is the arithmetic mean. That is the balancing point, right? Center of gravity of the histogram. Median, on the other hand, is the middle point, in the sense that when you put the data in the ascending or descending order, half of the data will be less than that approximately, and half of the data will be larger than that. So in that sense, it's actually the physical center, right? And then we discussed that the spread. When you want to talk about spread, especially when you want to talk about the spread around the mean, then we use the standard deviation. The other thing I will briefly mention, if you want to talk about the spread of the data around the median, usually what you do is, for a data set, suppose this is the minimum, this is the maximum here. Then like once you have the median doesn't have to be in the middle, like for example if the data, most of the data are like this and then only few some like this, then the median can be somewhere here, 50% can be here and the other 50%. Suppose the median was here, usually is called the second quartile. For a data set, usually we talk about quartiles. Right? There are three quartiles: first quartile, second quartile, third quartile. So the median is actually the second quartile. We denote it by second. So if you take the first half created by the median and you can find out the middle of this again. So this will be 25% of the data and this will be 25%, and then you can find out again another half of this data. So there will be 25% of the data here, 25% of the data here. Right? So that means you can find out 3 points, 3 values by which you can divide the data set into 4 equal parts. Right? So that each part will have 25% of the data. So this value here is denoted by Q1. This is the median, which is the same as Q2. This value here is denoted by Q3. So this distance here is called interquartile range. That is Q3 minus Q1. Q3 minus Q1. It's called the interquartile range. And you can interpret that as the range where the middle 50% of the data lies. Middle 50% of the data close, that is around the median. Right? Middle 50% of the data around the median lies within this distance. So in that sense, it gives you some idea about the spread of the data. Right? It gives you idea about the spread of the middle 50% of the data around the median. And then quartile deviation, I think it is divided as quartile deviation, that is taken as IQR divided by 2. That's called the quartile deviation, if I remember correctly. Right. But that is not, none of those is in this particular chapter here. Right. So that's what we discussed, and then we discussed that the mean, the relative position of the mean and median. For symmetric distributions, mean and median are roughly the same. For positively skewed distributions, mean is slightly larger than the median, and vice versa for the negatively skewed distributions. Any question from this section?
Why can't you use absolute values?
Absolute values can be used, but there is one disadvantage, that is, remember that these things are not used only for the sample calculations. Usually we go further and we have to make some inferences. Right? So if, for example, x bar, sample x bar is as calculated as the median of the sample, but it is also used as an estimate for the population mean. It's an estimate for the population mean. So there, after that, we usually talk about how accurate our estimate is. Right? So therefore we have to calculate confidence intervals and so on. Some more inference have to be calculated. So there, dealing with, for example, x bar and the squared distances from the mean, variance and standard deviation is mathematically convenient. For inferences, theory can be mathematically convenient. So therefore people usually talk about squares, distances and square root after that. So that is the only reason. Otherwise, dealing with absolute values is going to be mathematically complicated, somewhat difficult. So therefore many people don't like that. So that is the reason. Otherwise you can develop theory, but it's not that easy as standard theory that we have. Right? When we talk about square distances, there's some nice theory. Right? For example, from one distribution, from normal, we can get something called chi-square distribution and so on. Some nice theory follows from that. So therefore, people usually prefer that. Right? For absolute values, we can do, theoretically we can do, but the work are difficult. Therefore, people don't like it. So that is the only reason. Right? And also there are some other advantages also, because I have seen people talking about some other disadvantages of the absolute values also, which I don't remember exactly right now. Right.
Like the data would be 100% correct, absolute values. So it's better to take a range, something like that.
Range.
Like classes. Take the class and then take the midpoint and do the calculation instead of using the absolute values.
Now, yeah, that's correct. But what he asked was, instead of taking square values, why don't we take the absolute value?
Ah, yeah.
That's what he
The
asked.
one value.
Yeah, absolute value. Distance instead of, because values cancel out if you consider the without the sign, with the sign. So he is asking what happens if you consider without signs. That's what you asked. Yeah. So that can be considered, but because of the mathematical convenience, people use the other. Yeah. Right. So we have another half an hour. So let's talk about this one. The normal approximation. Right. That was what I was talking about, and about 60%, 68%, 95%. All those usually apply for normally distributed data. And in this chapter, actually, again, I am deviating a little bit from your book, because in the book they talk about only something called the standard normal distribution. But here I am just giving you, because you can handle more than that. I am going to give you more about the normal distribution, general normal distribution. Right. So this normal distribution is a particular model actually. It's not a real thing. We don't have situations in real life where the data are exactly so-called normal data. When you say normal, it's again confusing, because is that particular type is so-called normal and all the others are abnormal? That is a question that comes, but it's not like that. Some person has started calling it normal, and now everybody calls it normal. But actually normal distribution is not so-called normal, it's a very special type of distribution. But it's also called Gaussian distribution, to give credit to one important statistician. This is one of the most used models in statistics. So this normal curve was discovered by D. Montgomery while he was developing mathematics of chance and so on. A little bit of history here. So anyway, this is a mathematical curve that we can use to approximate some histogram. So this is the general formula for the normal distribution. It's a function of x. This is the mathematical variable. These two are some two constants. Mu is used to denote some constant. It's a fixed value. Sigma is another fixed value. So that sigma is appearing here, and this mu is appearing here. But this is the variable, mathematical variable. X can be theoretically between negative infinity and positive infinity. This fixed value here is for a particular distribution, for a particular formula. Mu is a value, single value, but that value can be again anything between negative infinity and positive infinity. This value is again a fixed value, but for this particular distribution, it has to be a positive value, or it cannot be negative. Right? But in the statistical terms, they have names. This is called the location parameter in general. This is called the scale parameter, location parameter, and scale parameter. Those are particular names here, right? So from your mathematical knowledge, if you have something like e to the power negative something like x square, right? Just forget about this number here and this whole thing. This just take, what kind of shape is this when x is from minus infinity to plus infinity? What kind of shape is this? If you have only this, yeah, it's very rapidly decreasing function. Right? So this one, this is so in that case, if x is negative, this x goes from a negative infinity to positive infinity, right? So when x is positive, is decreasing. When x is negative, yeah. So now, what is the shape of this in that range? Yeah, yeah. It has to go up and then come down like this. So it has that shape. So what is actually happening here is, because of this value here and this value here, is it's going to be first of all, this is going to be symmetric around this value, and its spread is going to be controlled by this value. So this is called the location, because it is it is symmetric around that value. This one is called the scale parameter, because it's going to give the scale whether it is going to be a very small spread or large spread. Right. So when you draw this thing for a given mu and given sigma, for example, if you take mu to be 50 and sigma to be say 5, two values, then this will be a bell-shaped distribution first of all, and it will be symmetric around this value 50. And roughly for this distribution, that 1 sigma, 2 sigma, 3 sigma rule applies actually. For this distribution, mu minus sigma and mu plus sigma, those two within those two numbers, for example, mu minus 5 is going to be 45 here and then 55. So in this area, there will be 68% of the whole area. Whole area is going to be 1 for this 100%. So if it is 100%, 68% is going to be between 45 and 55. Within 2 standard deviations from the mean, not the mean actually, I have just mentioned that with the center, from the center, it will be like 50, 40 here and then 60 here. So 95% of the area will be within those two. And then if you consider 3 standard deviations, 35 and then 65 here, that will contain 99.5, 99.7, 97.53 or something, very close to 1, and only very small, very small, 99.7 actually, area will be beyond that. So therefore, once you know the mu and sigma for this distribution, we can easily draw, using that idea, we can draw roughly a sketch. Right? So it has to be a bell-shaped curve, symmetric around 50, and roughly almost all the curve should be between 35 and 65. Almost all the curve. Right? Theoretically, it goes up to infinity, of course. Right? Theoretically, it goes up to infinity negative, but practically, almost all the area is between 35 and 65 for this distribution. So that is called the normal distribution. And later on, we can show that actually this center is actually the population mean. Right? If you draw this approximation for a population of values, and if the population histogram is symmetric, in that case, mu will be the population mean. And sigma will be the population standard deviation. Right? So therefore, this can be considered as the normal distribution with mean 50 and standard deviation 5. Normal distribution with mean 50 and standard deviation 5. Right? So there can be millions of normal distributions, depending on what the mean and what the standard deviation is. Right? So in a given situation for your data, if it looks like roughly a bell shape, then you can find out what is the most suitable model as a normal distribution for your data. Right? So you have to choose a suitable mu value and a suitable sigma value. Then approximately you have a model for your data, normal model. Right? So I have shown here several normal distributions with different means and different standard deviations. Right? So one particular very important normal distribution is a normal distribution with mu equal to 0 and sigma equal to 1. Right? So that is a normal distribution symmetric around 0 and roughly between -3 and +3. Because if you consider mu -3 sigma, sigma is equal to 1. So mu -3 sigma is 0 -3 and 0 +3. So that standard normal distribution. Theoretically it's going from -infinity to +infinity, but 99.7% of this standard normal, this is called the standard normal. Normal distribution with mean 0 and standard deviation 1 is called the standard normal. So that is like this. The total area there is 100%. Right. And this green one, I have taken mu to be 30 and sigma to be 5. So you can see that this green distribution is symmetric around 30. And if you look at mu -3 sigma and mu +3 sigma, mu -3 sigma is going to be 30 minus 15, that is 15 roughly here. And mu +3 sigma is going to be 45, that is here. So you can see that this curve is actually almost all the curve is between those two numbers. So like that, for any normal distribution, that property is there, right? Within mu -3 sigma and mu +3 sigma, almost all the area is between those two numbers. Now, if you look at the blue one, it has a separate, different mean, but the same standard deviation. Right? So therefore, you can see this one is symmetric around 30, but this one is symmetric around 60. Right? Symmetric around the value of mu. It has the same standard deviation, therefore these both have the same spread. Spread is the same. So you can see that sigma is the one controlling the spread. Mu is the one controlling the location. The same. Now if you consider this one and this one, you can see this one has a higher spread, that one has sigma equal to 10. These two have the same center, right? But this one has a higher spread. There again, if you consider 30 minus 3 times sigma, that is 0. So you can see that 0 is somewhere here. Somewhere here. So this curve comes up to that point, and then from the other side, 30 plus 30 is 60, right? Up to here. So from here to here, all the area is covered. So those are different normal distributions with different means and different standard deviations. What the book is talking about is actually the standard normal distribution. So the standard normal distribution is just a bell-shaped curve, symmetric around 0. Almost all the area is between -3 and +3. Theoretically, it goes up to infinity, negative infinity and positive infinity. But the area beyond -3 and more than +3 is 0.00. 0.0007 or something very, very small. Right. So this is that empirical rule that I mentioned for any normal distribution. This rule is correct. Right. Within one standard deviation from the mean, 68% of the area. Within 2 standard deviation from the mean, 95% of the area. Within 3 standard deviation, almost all the area. For any normal distribution. Right. So why do we need the normal distribution? Because in practice, there are a lot of situations where this normal curve can be used as an approximation for our histogram. Right? So therefore we just say our data have a normal distribution. Right? It doesn't mean it is exactly normal, but approximately normal. That's what we mean. We use it as a model usually. So here, if I go back to the previous example again, so even though the histogram is like this, it's pretty easy to, very clear, very closely it can be approximated by a curve. So what curve should we use here? We can easily find out roughly, okay, mean, it has to be mean mu has to be somewhere here for this particular curve. What should be the standard deviation? We can roughly find out this is almost all the area is between these two numbers. So this should be 3 sigma and this should be 3 sigma, altogether 6 sigma. So roughly we know what is the length of 6 sigma. So you can find out what the value for the sigma should be approximately. So if you draw the curve with that mu and that sigma, it will look like this. So therefore you can find out approximately. There are other better methods to find out suitable values for mu and sigma, but the easiest method is using the empirical rule. You can find out some approximate values for mu and sigma in that way. Right. So in the book, they are actually talking about the standard norm. Now, suppose you have some variable, say x, like heights of people who are 20 years of age, x. And if you draw that, if you draw the histogram, you saw that it is like a normal distribution. So suppose x has a, so this is how we say x has a normal distribution with some value mean, so let me denote it by some Greek letter mu, right? And SD some value sigma, right? So they are two numbers, right? So we can actually, if you look at this transformation, suppose we subtract this value from all the heights that we have and then divide by sigma to get like this, x minus mu divided by sigma. If you consider this transformation and if we call it Z, for example, you have new data. As a normal shape, bell shape, when you transform using this thing, again these are new data, these are transformed data. They will also have the same shape, but the center of this new data will be 0, right? Because you have taken away the mean. So new data will have mean 0. The standard deviation for these will be 1. Earlier x had standard deviation sigma. When you divide x by sigma, now when you take away mean becomes 0 here. When you divide by sigma, the standard deviation of this one will becomes 1. Right? So the distribution of Z will be then standard normal. Right? If x is normal with mean mu and standard deviation sigma, this new value Z coming from this transformation will have a standard normal distribution. Standard normal distribution. So, for example, what this transformation does, it actually we calculate how far away these x observations from the mean in standard deviation units. For example, suppose mu was 50 and sigma was 5, and suppose I had value 75, x is equal to some value 75, right? So if I calculate Z value for that, Z will be equal to 75 minus 50 divided by 5, so that is going to be 5, right? So what does that 5 mean here? This means this x value is 5 standard units away from the mean, right? This value is 5 standard units, 5 standard deviations away from the mean, right? So this is called the standard units after that, right? So the meaning of that is our observation is 5 standard deviations above the mean in this case, because you have a plus value. If you get a negative value, that means your observation is some number of standard deviations below the mean. So, so therefore, what this transformation does, it is actually it transforms the data into standard units. Standard units. Original units can be, for example, centimeters, or whatever, and these going to be standard units, and those don't have units. Z don't have units. For example, if x is in centimeters, mu will be in centimeters, sigma will be in centimeters. So centimeters will cancel out. These don't have units, standard units. They are called standard units. Right. So here are 2 examples. So if you look at the original histogram of the heights, right? you can draw it with this scale. These are actually heights in inches, and the percentage density, percentage for each. Right? If you convert these values, for example, into standard units, in this case the mean was 63.5. So when you convert that value into Z, it becomes a 0. 63.5 minus 63.5, and the standard deviation was, I think, 3. So if you subtract 63.5 and divide by 3, you get these numbers. Right? And then the density will be actually sigma times this density for the standard units will be sigma times the original units. Right? You can mathematically show it actually. Now, if your original distribution is something like this, for example, if you in x you write like it has this formula, 1 over root 2 pi sigma e to the power minus half x minus mu over sigma square. That is the formula for the original distribution. In this case, mu will be equal to 63.5 and sigma is equal to 3. So if you write down the density for the standard units, you can get it from the same distribution, same formula. What you have to do is, instead of x now, you have to put x minus mu over sigma. Right? X becomes x minus mu over sigma. Right? So it will be x minus mu over sigma and then mu and sigma. So what is the formula? Root 2 phi sigma, it will be still there. So e to the power minus half. Now x will be replaced by x minus mu over sigma, and then this mu have to be, and then divided by sigma square. That will be the formula for the standard density of the standard units. It's going to be standard normal actually, and then you can show that it is equal to 1 over root 2 pi sigma e to the power half. This will be just x square. Isn't it? Yeah.
You should substitute.
No, this has to be 0 here. This has to be 1, because when you subtract, when you x becomes x minus mu over sigma, then mu becomes 0, sigma becomes 1. So here you have 1 here. X minus mu, x becomes x minus 1, but mu has to be 0, this has to be 1. So this is the distribution of the original data, this will be the distribution of the new transformed data. This will be the, so this will be then 1 over root 2 pi e to the power, in this case actually this is Z, right? X minus mu over sigma is not x, it is Z. Z is equal to x minus mu over sigma. So if x goes to x minus mu over sigma, in this case for Z, the mean is 0, for x mean is mu. Right? So x becomes x minus mu over sigma. Mu in this case has to be, when you convert into Z, it becomes 0 and sigma becomes 1. So this will be the, you can write down Z if you want it. So that is the distribution of minus here. So that is the formula for the standard normal. So now if you want, you can look at you can look at the ratio. You can look at the ratio, and that will be just 1 over sigma. But if you multiply this by 1 over sigma, you get this, because this Z is the same as x minus mu anyway. Right? So the height, that's why you have it is mapped like 10 is mapped into 3 here, 20 is mapped into 60, 0 is mapped into 0. So it has been multiplied by 3. 3 is the sigma. I have actually written down that mathematics here. Yeah. So if you want, you can look at like that. So this is the original distribution. This is when you put x equal to x minus mu over sigma, that is Z, mu equal to 0 and sigma equal to 1, you get this one. So if you look at ratio, if you divide this by this, or you can see that this one is equal to sigma times this one. This is the standard normal curve, this is the original curve. So the standard normal height is equal to sigma times the original height. So if you want to read it from using the original scale, you have to read from this one. Or otherwise, the same can be considered in a different scale. In that case, this scale and this scale. එහෙම නැතුව මේක අපි මෙතන වෙනම අන්තනම් එහෙම 0 or -3 to this one, this distribution look like this height එක වැඩි වෙනවා. මොකද මේකේ මෙතන 60 වෙනකන් යන්න බෑ. මෙතන තියෙනදී 60 වෙනකන් යන්න. this scale එකේ අන්තනම් ඒ විදිහට. මොකද area එක අන්තිමේදී කොහොමද එක වෙන්නේ බෑ. area එක නම් this is 100%. The total area under here is 100. Here should be 100. So, but here the area is between this and this large area. Here when you convert it into Z, it will be by 15 minus 3 and plus 3, therefore it has to be total to cover the whole area. Right. So the book is actually talking about in that sense. So now we have 10 minutes. Let me talk about how to find out using a model, right? How to find out the probabilities or areas. So for example, suppose you are told that some random variable like height has a normal distribution with, for example, mu or the mean. Now notice here that the notation that I used earlier for the mean was x bar. If the data are denoted by x1 up to xn, you have a fixed number of n number of observations. If you calculate the mean of those things by adding the numbers and divide by n, that is called the sample mean. Sample mean is denoted by usually x bar. Here what I mean by mu is actually a population quantity, population mean. So these are two different things. No? We usually use the sample mean as an approximate value for the population mean. That is, we use sample mean as an estimate for the population mean, but usually there is a difference between those two. That's what we call the error of our estimate. Right? So in order to distinguish between these ones, usually we use two different notations. Right? When you talk about a model, we use the model for the population, not for the sample actually. We use the model for the population. So that's why we use mu and sigma in that situation. Suppose for our heights, population model, we are going to assume that in the population it has a normal distribution with some mean like say what is the 63.5 for example. That is our estimate. So we are going to assume that. And suppose sigma was 3. These are actually obtained from the sample, but we are going to use them as approximate values for the population quantities. Right. So suppose if somebody says like this, what does it mean? It means, it doesn't mean its population heights are exactly fitting a normal curve. Right? Even though we say x has a normal distribution, it means approximately we can use this particular normal distribution with mean 63.5 and sigma equal to 3 as an approximation to the population histogram. That's what we mean by that. Okay, now suppose somebody asks, given this, somebody asks, about what percentage of people will be between say 50 inches and 65 inches. About what percentage of people will be between these two numbers in the population. If somebody asks that question, then we can use that model to find out that percentage. Even though we don't have the picture or any data, if you are given only these two, then we can find out what percentage roughly will be in the population between 50 inches and 65 inches if we can use this particular model, normal model. Right. So how do we do that? If we have now, if somebody says like this, x has a normal distribution with mean, distance and deviation, roughly we can now roughly sketch the normal distribution. Right? It has to be between, it has to be centered around 63.5 and then roughly between, right, 63.5 minus 3 times 3 minus 3 sigma, and roughly here it will be 63.5 plus 3 times 3. So this will be roughly, so there will be a mathematical formula. Now the question is asking what is the area, in other words, right? What is the percentage? The percentage, total percentage is 100%. So what is the percentage between these two numbers? So 50 will be somewhere here, 65 will be somewhere here, right? So the question is asking what is this area? That is what the question is asking. So how do you find out the area? You know the equation for this thing, that is 1 over root 2 pi times 3 here, and then e to the power minus half x minus 63.5 divided by 3 square. That is the formula for this. So how do you find out this area?
Integrating from
Yeah, you have to integrate this from this value here to this value here. So that's what you have to do theoretically. But integration is not that easy here. So therefore, instead of directly integrating, we have another method. That is, first of all, instead of looking at this particular normal distribution, we convert it into standard normal distribution, right? So we convert this value 65 into Z value, this into Z value, and look at the area under standard normal distribution between those two Z values. Right? We can convert this normal distribution into, right? So this normal distribution has been 63.5. When we convert it into standard deviation, it will be between minus 3 and plus 3. It will be like this. So there is a value here 50, and that will be converted into some value on this one. That value will be what? 50 minus 63.5 divided by 3. This value will be converted into this value. And the next value I want is 65. That value will be converted somewhere here, right? So that will be 65 minus 63.5 divided by 3. Right? This curve have been converted into this curve. Right? So now instead of finding this area here, we can find out this area here. Right? And that area again find out how? You have to integrate standard normal curve. But we don't have to integrate it because people have done it for us, right? Because any normal distribution can be converted into standard normal distribution like that. So any area in any normal distribution that can be found out using the standard normal itself. So therefore it is enough if we know how to integrate the standard normal distribution, right? So even though we don't have to do it rapidly, so what people have done is people have tabulated the area under the standard normal distribution. We can get these areas from those tables. So that's what we usually do. Whenever we want to find out some area of some normal distribution, we use the standard normal table, we call it. Right. So let's look at that as an example here. So this is what the standard normal table look like. So this curve is supposed to be the standard normal density function distribution, and this axis here is roughly between minus 3 and plus 3, right? So it gives you area, this is what you want, area between some negative Z value and positive Z value under the standard normal distribution, right? It gives you that kind of area. For example, if you consider the standard normal distribution, the area between, say for example, negative 0.2 and positive 0.2, if you take Z to be 0.2, this will be here negative 0.2 and this will be positive 0.2. So the area between negative 0.2 and positive 0.2 under the standard normal curve will be equal to this value here as a percentage. So they have already integrated the standard normal curve between minus 0.2 to plus 0.2 and tabulated here. Right? So if somebody wants to get the area between some value and some value in their normal distribution, and if when they convert it into Z, it becomes negative value and positive this 0.2, then you can directly get it from the table. Right? But sometimes, for example, if we convert this 50 into standard value and this 65 standard value, they are not going to be negative and positive same value. So we will see how to get that. But anyway, the table gives you the area between negative Z value and positive Z value for different Z values. For example, if you want to find out, it's not clear here. If I look at, for example, Z equal to 2, for example, right? What should be the answer? We know that for the standard normal distribution, area between minus 2 and plus 2 should be roughly what? Standard normal distribution is symmetric around 0. Standard deviation is 1. Right? So minus 2 means 2 standard deviation below mean, plus 2 means 2 standard deviation above mean. We already know for the symmetric distribution like that, approximately 95% of the area should be between 2 standard deviation from the mean. So if you look at 2 here and area here, you can see that is 95.45. So that's what we mean by approximately 95%. Right? If you look at 3 standard deviation, right? Where is 3? 3 here. Right? So if you look at area between minus 3 and plus 3 in a standard normal distribution, that's going to be approximately 99.73% almost over the area. Right? If you look at 1 standard deviation, for example, 1, it has to be roughly 68%. We know already those 3 values. 1 standard deviation, 1. Very small. it was 1.5 का पार्ट थी हाँ नहीं मम मेरे में टेबल लेके उड़ा कोड से किधर नहीं डालती मैं कहता पाल है डियानो टेबल ले उते पाल है डियानो राइट मैं मुझे मेरे साइड लेके डाल दे मैं उड़ा क्या लेते डालती तो वो 1 value होते हैं if you look at the 1 value it will be roughly 68 point something here right so you can use that table to find out actually any area under any normal distribution. So let me take 1 or 2 examples. Right? Only what we need is that table. So actually these are called standard normal tables. In different books, these tables are given in different ways. In some tables, they give you the area, all standard normal distributions are roughly between minus 3 and plus 3. But some tables give you the area above some Z values. These type of areas are given in the table. Right? Some tables give you the area below a given value. Right? So Z value will be here and then area below that is given. Right? So depending on the table you have to find out what that table actually gives you. Right? So if you use this table, let's look at some examples. Right. So let's look at the previous one to find the area under the normal curve between -1. So this is directly to find out the area between -1.2 and some other value, right? For example, if you want to find out -1.2 and positive 1.2, directly you can read the table for the standard normal. Right? So -1.2 and positive 1.2, 1.2 again not in the table. Make it පල්ලෙහා කොටස තියෙන්නේ කියවුවොත් එහෙම ඉන්නේ 0.77 කියන මේ විදිහට. ඒ වගේම මේ වගේ ඒරියා එකක් හොයන්න වුණොත් ස්ටෑන්ඩඩ් නෝමල් ඩිස්ට්‍රිබියුෂන් එකේ ඒතර කොහොමද කරන්නේ? අපිට දීලා තියෙනවා අපිට ගන්න පුළුවන් නෙගටිව් 1 සහ පොසිටිව් 1 අතර ඒරියා එක නම් ගන්න පුළුවන්. හැබැයි අපිට ඕනේ මේ ටික විතරයි. So we find out the area between -1 and +1 from the table and then take half of that because it is symmetric around 0. If you want to find out asymmetric area like this, if you want to find out negative area between -2 and +1 in the standard normal distribution, what you have to do is, right, you know that area is equal to this area plus this area. Right? So this area is equal to half of the area between -2 and +2. This area is again half of area between +1 and -1. So by using those two, by adding those two, you can find out the area. So it's 82%. So like that, you can find out any type of area using this table. So what you have to do is, if you are given that x, this is how you write down notation using the notation x has a normal distribution with mean 50 and standard deviation 5. This is the standard notation. Usually in the standard notation they write down mu at the first number. Second number they write down actually the variance, not the standard deviation. So if the standard deviation is 5, they write down here 25. So this means x is some random variable. It has a normal distribution with mean 50 and standard deviation 5 or variance 25. So suppose you are considering some model like that. So therefore in this case you have this kind of normal distribution with mean 50, and then roughly between what and what will be the almost 50 minus 3 times 5 is 15, that is roughly 35, and then 50 plus 15 is 65. Right? So roughly this distribution is like this. Right? Suppose you want to find out the area or the percentage between say 40 and 60. What is the percentage between 40 and 60? So what you do is you convert this value into standard normal, standardized value. How do you do? So this is for the 40 z value will be 40 minus mu divided by 5. So that will be the corresponding z value. And for this one, corresponding z value will be 60 minus the mean divided by 5. Standard deviation is 5. So there is going to be 2 and this is going to be this is -2, this is +2. So now instead of finding the area between 40 and 60 for this distribution, what you have to do is find out the area between -2 and +2 in the standard normal, and that can be obtained from the table. And similarly, whatever the values you get here, then corresponding z for the corresponding z values, you can get the area for the standard normal. So that's how you find out the proportions, or if it's a proportion, is going to be a decimal number as a percentage using a model, right? So here we are using a model here, right? So I have given you an activity. Please do it at home. This part is actually repeating the same idea. So please go through that. And then percentiles. Percentiles are really required actually when you want to talk about interquartile range, and even when you want to find out the quartiles. Percentiles. In a histogram, using a histogram, you have, for example, a normal distribution. This value here, whatever this mean, is actually 50th percentile. So that means the area below this is 50%. So this value here is the 50th percentile in a normal distribution. Mean and median both are, population mean and population median are the same. So similarly, if you find out some value here, so that this area here is say 10%, so then this value on this axis is called 10th percentile. 10th percentile. So like that's how you define the percentiles. The area below that number, right, has to be whatever that percent. Right. So those are called percentiles. So as I mentioned earlier, quartiles. If you take quartiles, first quartile will be the same as 25th percentile, right? Because area below this thing will be altogether 25%. And then this is the same as Q2 for the population, that is the 50th percentile for the second quartile. and then Q3 is the third quartile. Area below that is 75%, therefore that is the same as 75th percentile. Okay, so in order to find out the percentiles, actually you have to read the table the opposite direction, right? Once you know the Z values, you can find out the percentages, and then once you know the percentages, you can find out the Z values. And I leave that for you to think about how to do it using this particular table. It's not that difficult. Right. I think I'll stop there today. I have to go actually. I have to take my son from the class. Yeah, because otherwise I would like to